Assalamualaikum and good day everyone. So today we will continue about our lecture on magnetic material and influence. Okay, we will touch on the introduction to the concept of inductance, application of energy density and energy storage within a magnetic field. Okay, before I start with the lecture, okay, I want to rectify something. There is a bit typos in my previous lecture for the magnetics on the in the boundary conditions. Okay, so here for boundary condition there is a typo. Okay, here it should be in bracket. Okay, this one should be in bracket. Okay, for the tangential components. Okay, h1 minus h2 cross with the normal vectors. Okay, so this bracket means, okay, so I hope this will clear up. Okay, so we will continue now to this week 11 lecture. Okay, week 11 lecture. We so you may refer to the Sadiko books. Okay, today is 29th of May 2021. It's around 10:50 p.m. Okay, so we'll touch about the inductor and inductances. Okay, application of energy density, energy storage within a magnetic field. So in the Sadiko books, you may refer to page starts from page 387, okay, and above. Okay, so without further ado, we may start, okay, to discuss about these issues. Okay, so a circuit or closed conductive path, okay, will produce I, right? In the electrostatic, we are concerning about the charge. However, in this magnetic, we are concerning about the current. So we have a circuit, for example, or even a line current. Okay, we have a current I. Okay, we have current I. This current I will produce a magnetic field, which is your B. Am I correct? Okay, that causes a flux. So we have discussed in the previous lecture. Let me see. Okay, we discussed in previous lecture that this magnetic current carrying current produce a magnetic flux that will in turn will produce flux, just like in your in electrostatic we produce flux, right? But the one is electric flux, okay, which is in relation with your with your D. So here your flux, okay, your flux we can put M, depends on you, as long as you understand what is it. We know that it is a dot vector of B and ds. Okay, to pass through each turn of the circuit, so we have this flux, and it is like a closed flux. Okay, if the circuit, if we have in the circuit carrying current, if we have n identical turns, okay, turns. Let's say our turns is, we give an okay, let we see the circuit first. Okay, when we have this one, okay, so this is a turn, number of turn, right? So this number of turn we can refer to as n, and we have this as our current carrying, okay, and there is voltage source, okay, and you will produce an you will produce magnetic field, okay, which is signified by your B. Okay, and from here you will produce the magnetic flux, right? So here is, okay, you can see like this. Okay, so this is flux produced from this. Okay, so we define the flux linkage, we can define as flux linkage as lambda. Okay, you may refer also to the slides, okay, to the slide lecture slides. Okay, lecture slide week 10, you can start referring to slide 23. Okay, so continue. So if we have n as our identical terms, then the flux linkage, okay, flux linkage lambda, okay, is equals to n over your flux. Okay, so if the medium surrounding circuit is linear, okay, we also know that this flux linkage is actually proportional to the current producing, okay, with the current that we are producing. So we have lambda is actually proportionate to your I, okay, and from this lambda and I, if we want to make an equation, we need to produce a constant, right? So here the constant would be L, okay, L with your I, okay, I mean the constant is your L. So what is the L? L is actually what we're referring as the inductance of the circuits. I think you're a bit familiar with the word inductor, but you maybe inductance is not really familiar for this EM. I mean, this quite new, right? Just like how we approach in resistance is like general terms. You can have resistance in circuit V equals IR, but in field theory is different, right? But they are still the same, which is resistance. So here might be a bit different from the conventional, but we will learn through, okay, together. Okay. So what is actually L? L is the inductance. Is actually the ability for the this physical to store physical arrangement to store magnetic energy. Okay, like this is the physical arrangement. Okay, now so we may further extend this equations of inductance, okay, by relating it with the magnetic flux linkage and also the current through the inductor, okay, and also with your N, okay. You know L is equals to I lambda, okay. So I think my battery is a bit low, so let me sorry. Okay, I think it's okay now. Okay, so let we relate. Let's say we make this one as the main equation here. You put your L here, okay, rearrange. Then you have your lambda over I. Am I correct? Okay. And then you know that lambda is equal to N flux. Okay. So we may further extend the equation. Is actually you have N flux over your I. Okay. So this is first. This is also the equation relates. Okay. Okay. The units of inductance, I think you guys also know about this. It is in Henry. Okay. The unit is in Henry, which is the same as we can also use Weber per Ampere. Okay. The other units of it. Okay. I think this is confusing. Let me rewrite. Is Henry or Weber per Ampere. Okay. Since the Henry is usually, if you notice, when we use inductor in our circuits or whatever components that you experience in school, normally we don't use Henry directly. Normally we have like millihenry, microhenry, something. Okay, but the often unit that we normally refer to it is normally we refer as millihenry. Okay, I think this one is quite straightforward. Everyone knows. Okay, And then the inductance is inductance is normally caused by self-inductance. Okay, self-inductance, because the linkage is produced this by the circuit itself. So when we can express the magnetic energy stored in inductor, okay, we can express it into our Wm equals to half of your Li square. Okay, if you rearrange to relate it with your inductance, okay, you will know that L is also equal to 2Wm over I square. Okay, so this is just rearrangement. Okay, and then for example, I think from Sadiku, okay, I will do summarization, but you can read from the detail from the Sadiku. Okay, so let's say we have circuits. Okay, from the Sadiku book, let's say we have circuits. Okay, so when this is current producing circuits, okay, a circuit producing currents. For example, you have your I1 and this is your I2. Okay, when you have current producing circuit, you will start to have magnetic field. Am I correct? When you have magnetic field, you also have magnetic flux. Okay, so let's say you have magnetic flux to circuit. This one is your, let's say we give the name first. Okay, this is circuit 1. This is your circuit 2. Okay, so let's say you have flux which running through coming from circuit 2 towards circuit 1. Okay, means the flux passing through circuit 1 due to current producing in I2. Okay, let's say you have here. Okay, so this is referred to as flux 1, 2. Is that flux passing through circuit 1 due to current I2. Okay, so the numbering you can see. And then of course similarly, you will also have a flux passing through circuit 2 due to current passing through circuit 1. Okay, so we have another flux then. Which is flux passing through circuit 2 due to current producing in circuit 1. Okay, so you know that your flux is actually BDS, right? Vector BDS. Okay, in this circuit you will have 4 component of fluxes. Okay, you can have 1, 1, another one, 1, 2, 2, 1, and 2, 2. Okay, and if you want to relate with these equations, okay, you may have flux 1, 2 is equal to S surface of 1, okay, because it's passing through circuit 1, and you have B2 because this is coming from because this 2 is actually coming from the circuit 2. Okay, and then you have DS dot products, and remember it is a vector. Okay, and then we define, okay, and then we come across the, I think in school you also get to know about the mutual inductance. Am I correct? So here we also have this mutual inductance. So we define the mutual inductance as the ratio. So first you have mutual inductance. What is mutual inductance? Mutual inductance is what is the ratio of flux linkage. Flux linkage over the current. Okay, over the current. So let's say if we have M21, okay, if your mutual inductance M12, okay, this capital M. So what is it? Is actually the flux linkage, where you see your flux linkage just now is here, right? Okay, which is which also you know that lambda, I try to see the equation because I write it. Okay, here. Okay, flux linkage is lambda. So lambda equals to m flux, okay? So this is M12. So here is actually lambda 12 over I2, okay? So further expand this equation from these equations, okay? So you get N1 over flux 2 over I2, okay? So you need to know the meanings of this, okay? So this one is quite straightforward, because this one is mutual inductance experienced by one due to current passing through I2. So that's why we have the same here. This one is N1, okay? And this one is flux, okay? Sorry, I forget to write 1, 2, okay? So this is I2. So this is your mutual inductance. I hope if my phone have no memory problem, we can try. We can try some examples. Otherwise, I have to upload this one video. I mean, I have to upload this video. Maybe take some time, and then to upload it to internet. And then I cannot delete this from my phone unless I'm sure that it is successfully uploaded to internet. Okay, and then if we have. Then if I settle with this, if we have some more memories, I will record the example, okay, if possible, okay. So you have this M12. How about this one is mutual inductance for on this circuit 1, okay. How about if we have mutual inductance in circuit 2? Okay, you guys can always report from the Sadiko. Okay, I'm just doing the summarizing. So similarly, it will be like this. Okay. Okay. We also get to know that if the circuit using energy concept, if the circuit is linear, okay, if the circuit is linear, surrounding the circuit is linear, in the absence of, for example, absence of ferromagnetic material, I think we learned from the previous lecture, okay. This one is considered as linear, and this one is considered as non-linear. Okay, for materials which is linear, it is diamagnetic or paramagnetic, okay. It is non-linear if it's ferromagnetic. So in the absence of ferromagnetics, okay, because ferromagnetic is the non-linear, so in the absence of the ferromagnetic material, if the medium surrounding that circuit is linear, okay, we may also shown that M12 is actually M21. They are equal in the absence of ferromagnetic material, okay. Then we also know that the total energy, we can also make a total of this energy is the sum of the energies due to your inductance 1, okay, and your inductance 2, and also the mutual inductance, okay. So where you know that for flux 1, okay, flux at circuit 1 is actually coming from flux 12 plus flux 11. Am I correct? Because this one is flux coming from the circuit 1, and this one is flux coming from flux due to current producing in circuit 1. This one is flux due to current producing in circuit 2. So this is your flux 1. Similarly, for your flux 2 is actually flux 21 plus flux 22. Okay, am I right? Okay, then this magnetic energy, total energy in magnetic field, Okay, total energy in a magnetic field. Okay, we have Wm equals to W1 plus W2 over W12. Okay. So what is W1? I try to, okay, see the good color. So half of Li I1 square, okay, in magnetic total energy in 1, okay, and then we have half of L2 I2 square and half plus minus of your mutual inductance I1 and I2, okay. And then you see from the Sadiko, it is mentioned that, sorry, the positive sign is taken if current I1 and I2 flow such that the magnetic field of the two circuits strengthen each other. If the current flow such that the magnetic field oppose each other, the negative sign is taken. Okay. In your slide that I share with you guys, so we have touched on this, okay, briefly, okay, where the energy that involving this inductance is actually W equals to half of Li square, okay. Because it is energy, what is the unit for energy? Is this joule? Am I correct? And then this L and I, Li square for the energy calculation also can be expand, okay. Further, also can be expanded to half of, for example, if you want for considering the continuous, okay. So the is B dot your H, okay, and dV, okay. And this one you can actually extend it again, okay, because you know B is actually B equals to mu H, am I correct? So if you want to extend it again, that's why you will have mu H, okay, dV, which end up as half of mu H square dV, okay. And then for the step, if you want to resolve problem regarding regarding self-inductance L or anything about self-inductance of L, first, of course, similarly in most of the cases where we want to try to solve electromagnetic problems, we need to find a first we need, okay, step by step for if you want to find everything involving this self-inductance, okay. So first step is actually we need to find the coordinate system suitable, okay. If you end up with not really suitable coordinate system, you may find that you take a long step just to solve it. It will be lengthy than usual, than supposed to be, okay. So you need to choose this coordinate system, the suitable one, and after that you will identify your inductor carrying current, okay. 3, you will determine you find your B, okay, from which you can have from two kind of situation, right? First, you can have from your Biot-Savart law, This is just like a Coulomb, the conventional way of convert Coulomb force, okay? But analogous, okay? Analogous because this one is magnetic field, and or like in electrostatic Gaussian law. So here we have Ampere circuital law, okay? Ampere circuital law, where we will, we will have Amperian loop whatsoever. However, the condition for this, just like in the Gauss law, okay, we must make sure that this one only apply if symmetry is exists. Otherwise, you cannot use this, okay? Just the same as electrostatic field, okay? Symmetry and in electrostatic symmetry and uniform charge distribution, okay? So similarly with Ampere circuit law, symmetry must exist, only then you can able to solve this B, determine this B using Ampere circuit law. And the fourth, which is the fourth step, is actually we will find our L, okay? How we find our L? It is from L equals to lambda over I and N flux over your I, okay? I would like to remind that maybe the slide and the book may have different way of expressing, but it belongs to the same thing. Just like in Sadiko, it is using JB, okay? But if I'm not mistaken, okay, and the slide is using KB, but it still refer to bound surface current density, or you can call it bound surface magnetic current, okay? As long as it says we know that it's a bound surface, okay? You can use KB or GSM, okay? I hope that you guys don't get confused. Okay, so there you are, okay? In order to find your step by step in solving something related with self-inductance or I, right? Okay, or L, sorry. Okay, and then when we talks about inductance, we also know that actually there is total inductance. Total inductance, it is shown by coming from the internal, okay, internal, plus with your inductance coming from external, okay? So this L external, you can find it from C over mu epsilon, okay? What is C? C is your capacitance, okay? Okay? So next, we go for the other parts of this supposed to be covered in this week lecture. Is your magnetic energy, okay? So wait for a while. I make some. Okay. So the next is about this magnetic energy. So you have learned that from the magnetic energy, here W equals to Li square. Okay, so it's the same. Okay, you have W equals to half Li square. Okay, but we will just going to explore it further. Okay, so this is magnetic energy. So Wm equals to Ym is magnetic. Okay, have half Li square. Okay. I think you also learned in the potential energy for this electrostatic. Okay, So you can refer to equation 4.95 for electrostatic. I don't want to mention about electrostatic too much because otherwise you get mixed up, because this is about magnetostatic. Okay, and then if we want to express, okay, because this is just like in electrostatic where it is about, okay, I just want to mention briefly, just like in electrostatic is about D, about E. Am I correct? So here in magnetic energy, we want to relate, okay, we want to relate with your B and with your H, okay. So if you want to relate with the B and H, okay, which is already covered previously here, okay. Okay, constantly I covered it as well. So it's actually, you can refer to it as half of your BH dV and also half of mu H dV, okay. And then from the study cookbook of page 391, okay, you may see formula of inductance for different kinds of common elements, okay. Let we discuss here instead of I'm writing, okay. So you can see this, okay. So you can see common element, a lot of them in various shape. For example, wire, hollow cylinder, parallel wire, coaxial conductor, circular loops, solenoid, torus, sheet. I hope that you guys can actually took your time to understand each one of these, okay. I think this is quite straightforward. You see this one is mu naught, and L is due to the length of this wire, and you have lambda. Then after that, in the coaxial conductor, you have L, mu naught L over 2 lambda, or 2 pi over ln over B over A. So if you do the exercise, okay, if you do the exercise, or you will get to, when you solve, okay, when you solve this half of Li, I mean when you want to solve this, you will end up with this, okay, ln B over A. Okay, hopefully we will cover that, or otherwise I will share to you, okay, the video by the lecturers where actually they solve one of the exercise where they come to produce this kind of ln B over A, okay. There is video lecture on this where I actually watch it, and I hope you guys please take your time. Again, I'm reminding again to watch the other lecture video, because they already have collection of past lecture video they have made. So don't waste it. Make use of it, okay, to help your study, okay. Okay. So because it is about V, okay, you can see it's about dV, which is the differential volume, okay. For example, in this conducting sheet, okay, wait for a while, I adjusting. So you have this one is certainly is Cartesian coordinates, right? So because it's differential volume, so we have differential of x, we have differential of y, and differential of z, okay. So you can see that, okay, I think you guys can read this on your own, okay, because in the end it will produce, this your energy that we have touched before, okay. So this dV is actually solved depending, as I think you already know, is depending on the coordinates, suitable coordinate used, okay. So it can be your Cartesian, cylindrical, or spherical, okay. Now we just get through this example at 0.13 first, okay. Calculate the self-inductance per unit length of an infinite length long solenoid. Okay, when it is infinite, what we can deduce is that we can use Ampere circuit law, for example. Okay, if you want to solve it. Okay, so we recall, for example, 7.4. I don't want to refer to that 7.4. You can read. Okay, 7.4. The magnetic flux inside the solenoid per unit length is B equals to mu hash, and U equals to IN. Okay, because I is your current, and N is actually the number of turns per unit length. N is equal to N over L. Okay, if the S cross-section area of solenoid, the total flux through the cross-section, which is this one, you know, flux equals to BS. Okay, the equation just now. Okay, we get from this BDS. Okay, flux BDS. Then B and S, and this B is taken care from this is mu over equals to B is equals to mu I and N. N is actually the ratio, okay, between your capital N over your length. Okay, here. And S is of course the surface involved. This surface is what will depends on will sort of depends on the coordinate that we want to use. Okay, since the flux is only for unit length, that's why you need to divide by L. Am I correct? Because it's mentioned per unit length. So lambda, okay, lambda for your self-inductance equals to lambda over L, okay, which is N flux. Okay, N flux. Okay, here lambda equals to M flux because it's involved with per unit length, so lambda over L. So this one is over L as well, M flux over L. So M flux, okay, N flux equals to this equation, okay, mu N, which is the ratio IS, and thus the inductance per unit length is actually L prime mu N square S. Okay, so hopefully I will touch on the exercise as well. Okay, I mean to demo some exercise. Okay, but I have to proceed first with the lecture so that to make sure that I have sufficient memory for video. Okay, so you get to you get introduced to these equations. Okay, okay, please try to read the example. Okay, when you read the study book, you try to read the example and you try to do this practice exercise. Okay, and there is answer given. Okay, I will maybe do this one later on if I have available time, and hopefully I remember, okay, to show it to you. And then you also get introduced with this when you solve, okay, this situation for the coaxial cable of inner radius A and outer radius B. Try to understand, and then you will come across that L equals to mu over 8 pi. Then after that you extend it again. Okay, please read the explanation. It's very detailed, it's very good. Okay, so you could put detail on this. Then you come across mu over 2 pi, half of ln BA. Okay, and then these books they solve using two methods. Okay, but you see there's there's two methods, but the answer should be the same. Okay, so okay, so you see just now it is related to this equation. Okay, mu naught L over 2 pi ln B over A. Okay, because it is about the question is about determine the self-inductance. Okay, determine the self-inductance of coaxial cable. Okay, So if you see from these equations, okay, they are considering both internal and external, okay. So this page on these magnetic circuits, okay, I think is let me see. So it is okay. We are learning until application of energy density and energy storage only. Okay. This one you guys can read for further understanding, okay, if you interested, okay, magnetic circuits, okay, and this one is the analogy, okay. So I try to upload this video lecture first, okay, and to hopefully that I have memory left after. I mean, I need to upload and make sure that I successfully upload to YouTube, and then only then I can delete. When I only if I able to delete, then I able to record new video. So it might take some time, okay. So what we have learned on your week 11, okay, is this, okay. Let me okay, I think you guys can see the overall, and please watch the supplementary video. Sometimes okay, if you notice, I'm quite late in linking to the supplementary material, but you guys can see they already put it in they already make a playlist according to week. So it's already made easier for you guys to learn. There is exercise, there is also lecture, which I think some of them or most of them is better than my explanation because they are coming from experienced lecturers. So don't waste their knowledge, okay, whatever they're teaching, don't waste it, appreciate it, and use it, okay. And so with that, we will continue with the next lecture, okay. Thank you very much. Assalamualaikum and good day.